In this video, we are going to work on example 6 and example 7. These two examples are the last of lecture number 10. But keep in mind that we still have lecture number 11, 12, and 13 to come. But that is for the future. For now, let's just focus on this lecture and this slide in front of you. So example 6, it's asking you to calculate the area enclosed by the domain region of example 5. So this is related to example 5. If you can't recall what we did in example 5, please go back and watch the previous video. Otherwise, this example 6 is not going to make any sense. So in example 5, we have this domain region. So let's bring that domain region back here again. So in example 5, we have this graph. Okay, so we have y-axis like this, and we have x-axis right here. And then we talk about the domain region, and this domain region is enclosed by some lines. So let's take a look at those lines. So the first one is y equal to 2 square root of x. The next one is y equal to 4x minus 2. And the next one is x-axis. So let's draw these lines on the graph. So the first one, which is the y equal to 2 square root of x, and this is going to look like a parabola on the side. So it should look something like this. Okay, so that is the first line. Then we draw the second line, which is the y equal to 4x minus 2. And as you can see, this is a straight line with a slope of 4, crosses the y-axis at minus 2. Before that, let me put the y-axis and x-axis here. Okay, crosses y-axis at minus 2, maybe around here. And this graph is supposed to be quite steep because of the slope of 4. So it should be something like that. Okay, so that is the second line, and we also have the third line, x-axis. And of course, this is easy to find right here, x-axis. Okay, doesn't look good, so let me do that again. X-axis. Okay, this is better. And you can see that with these three lines, they trapped a region between them, and it's shown on this shaded area. All right. And that's what we found in example 5. We also found that this intersection point right here is 1 over 2 and 0 at this coordinate. And up here, another intersection at x equal to 1 and y equal to, x equal to 1 and y equal to 2. Okay. So we have this domain region in example 5, but we didn't stop there. We performed some computation, and that is the double integration. So we did the double integration of the function surface, which is the 16 minus x squared minus y squared. And we perform this double integration over this region that we just draw on the left hand side. So we put differential area here, and we do that over the domain region. So let me clear this. We need more space. So we perform double integration of 16 minus x squared minus y squared over this region R. And in this lecture number 10, we have done many double integrations. All these 5 examples, it's all about the double integrations. We did the double integrations over rectangular domain, which is quite straightforward to do. And then we also did the double integrations over the general idea in the last video. And so far, we have established so clearly that when it comes to double integration, it's about the volume, right? Volume under, not just any volume, it has to be the volume under the function surface. Under function surface, and we are going to use fxy here, that is function surface. And not just the under function surface, it has to be above certain base, and that base is the domain region. Under F over domain region, which is R. Why do I have to talk about this again? Because the keyword for example 5 and example 6 is quite different. So let's take a look here. In example 6, we are supposed to find the area. But in example 5, we found the volume. That is the main difference, and it's totally different things, right? Volume of an object, an area of a region. So you might ask, when it comes to area, this area, isn't it supposed to be associated with single integration? Something that we learned in Cal 1. In Cal 1 we learned that definite integral is the area under the graph. And now we learn in Cal 2, why are we talking about the area here? It turns out that area, area can be calculated by both single integration and also by the double integration. So in this example, we are gonna find a way to use double integration to find the area. Use double integration to find the area. So how is that going to be possible? Let's take a look here. So to understand this, we need to travel back in time to maybe high school or middle school. In order to find a volume of an object, well, simple shape object, volume, we use this formula. Volume is going to be equal to the area of the base of your object times the height of your object. Area of base times the height just like this. We see something like this in high school, right? We have the height, or this drawing is so bad. Okay, sorry about that. Okay, we have this area at the base, and then we have this height. Okay. Once the area times the height, you get the volume of this post. Okay, so that is what we know from high school. But in Cal 2, we switch things around a little bit. So instead of using this simple formula, we use this instead. Area of the base times the height of the function. So instead of using just the height, we use the function surface value, fxy. So in this case, I want you to think back about what we learned in the beginning of the class after the midterm. We visualize the surface, and then we see the volume under it, and we also see the area, see the base and the area. And we also know that when it comes to this, area times the height of the function, this is equal to the double integral, fxy over a certain region, this same region, area of the base, right, R. Same thing. And with this is going to be equal to volume. But in this example, we don't want volume, we want area. So we are going to modify this. We are going to modify this this expression to work with just the area. Alright, so let's take a look here. Let's take a look at this green box. What if I set the function value here to be equal to 1? This to be equal to 1. And if this fxy equal to 1, it means that the other side has to be equal to 1 as well. So if we do something like this, what's going to happen? Let's take a look. So on this side, this is going to be the double integration of fxy. Oh, sorry, not fxy, it becomes 1 already. So this double integration of 1 over this region is going to be equal to the area of the base times 1. So basically this is equal to the area of base. Well, this is times 1, but it doesn't matter now, it's just 1. So here we have a modified formula, and you can see that you can find the area of the base, which is the domain region, and you can find that by using integrals. Use double integrals to find area. Well, different from before we find the volume, but here with this we find the area instead. And if you look at this, the main point, the main difference between this and the formula that we had before, the ones from Fubini's theorem or the from number 1 or number 2, is this 1. Alright, all you need to do is to set the function value to be 1, and the result is going to be the area of this base. Alright, so this is going to be what we use in this example to solve for the solution. Alright, so we have this formula ready. So let's do the integration. Alright, so we have this this formula, double integration of 1 over the area. Alright, and this region, and it's going to be the area that we want. Okay, now in this case, since the problem doesn't tell you the order of the integration, you are supposed to determine the type of the region that we are working on. So type, what is the type of this? Actually, we already did that in example 5, but let me rephrase it here. Repeat it here. We have this shape, alright, and we have this line, okay, something like that. And in example 5, we show that it's supposed to be sweeping along the x-axis first, sweeping horizontally. It's easier to work with. So in this case, this is type 2, sweeping horizontally. Well, in example 5, I show another way to do this by sweeping vertically, but it's more difficult. So if you want to choose the easier way to solve this problem, well, pick type 2. So here type 2, which means that I'm going to need to integrate this with respect to x first and then y. In this case, the function value is supposed to be 1 because we want the area. We don't want the volume, just like before. So with this, we are supposed to specify the left-hand function, that is g h1y, okay, and the right-hand function, that is h2y. And also we need to specify the whole range of y, so from c to d. Okay, now in order to continue, we need to know what these values are: h1y, h2y, c, and d. So h1y, this is left-hand function, left, and h2, this is right. Okay, so from before, we know that the right-hand function, so let's start with the left-hand. Left-hand function is this, y equal to 2 square root of x, but we want a function of y here, so we need to switch things around. So this becomes x equal to y squared over 4. So this equal to y squared over 4. Now the other lines, y equal to 4x minus 2. But for this, h2y supposed to be expressed in terms of y, so we need to switch things. This x becomes x equal to y plus 2 over 4. Alright, and from the range that we found from the intersection, this y value ranges from 0 to 2. Now let's put all these numbers in. integrate twice. The first, starting from the left hand function, which is y squared over 4, ends at the right hand function, which is y plus 2 over 4. And we are going to integrate just one value here. With respect to x first, this is type 2. Respect to x first, and then respect to y over the whole range, and the whole range is 0 to 2. Okay, after this, it's just the integration. So let's do that. Let me put some boundaries here. Okay, so this is going to be equal to, so integrate 1 with respect to x, this becomes x. And we have to evaluate this at two values, y squared over 2 over 4 and y plus 2 over 4. And then we still have to integrate this with respect to y from 0 to 2. Okay, so let's put all these numbers in. Y plus 2 over 4 goes in as x, minus y squared over 4 goes in as x. And then we are supposed to integrate this with respect to y at the end. Alright. Okay, we have limited space here. So as you can see here, we have common terms. I'm going to take the 1 over 4 out so that the calculation becomes easier to work on, to work with. So 1 over 4, integration of 0 to 2 of y plus 2 minus y squared. And integrate this with respect to y. So this is equal to 1 over 4. And this equal to y squared over 2 plus 2y minus y cubed over 3. Now I have to evaluate this at 0 and 2. And as you can see here, if 0 goes in, everything is gone. So I just need to put 2 in. So 2 squared over 2, that's 2. Plus 2 goes in as y, this becomes 4. And minus 8 over 3. And well, you can put 0 in and you are going to get minus 0 anyway. So here, if you work this out, it's going to be equal to 1 over 4. So 2 plus 4 becomes 6. And 6 is equal to 18 over 3. 18 over 3 minus 8 over 3, this becomes 10 over 3. So the result of this calculation, so you cancel this 2 and 5, so you have 5 over 6 for the answer of this example number 6. Well, don't forget to put the unit too, because they ask you for the area, so put square unit. So this is more complete than just 5 over 6. Alright, and that's how we use the double integration. Well, it all comes to this formula. Use double integration to find the area of a region. You can do that too. Well, in this case, you can also use the single integration, but this is just another option for you. Okay, now the example 6 is done. Let's move on to example 7. Okay, so what is it asking from us this time? So in this example, let's take a look here. They want us to calculate the area. Okay. Well, area enclosed by what curve? The first curve is y equal to x squared, and that is a parabola. And another line, y equal to x plus 2, that is a straight line. So why don't we try this new formula that we just found in example 6. So we are going to use the double integration of function equal to 1. So let's do that. So the formula is this: double integration of 1 over the region, right? And that's going to be equal to the area that they are asking for, the area. But the thing is, with this, we have to rely on the Fubini's theorem number 2 So in other words, we need to choose whether we are going to use the formula 1 or formula 2. So in other words, well, we are supposed to determine the type of this region. So determine type is the first thing we need to do. And to determine the type, the only way to do that is to draw the graph. So let's draw this graph. Alright, so we have this y-axis. Okay, and then let's draw the first line, the first equation. That is y equal to x squared. So it's going to be a parabola. It should be something like this. Okay, let me fix this really quickly. Okay, so this is the first line, parabola, and then we also have another line, a straight line, crosses the y-axis at 2. So maybe around here at 2, and the slope is 1. So something like that. Okay, so when you look at these two lines, you can see that they trapped a region between them, just like before. So this region, shaded area here, we are supposed to compute the numbers, the area numbers. So if it's up to me, when I look at this, I see right away that I have this one function at the top, okay, and another function at the base. That's how I see it. Okay, and when you see it this way, it means that you are supposed to sweep from the lower function to the upper function like that, and you repeat it throughout the region. So when you look at it this way, this is type what? Type 1, because you sweep it vertically. Alright, so that's how I see it. But if you are not sure about this and you don't see it like this, maybe you can try doing this by try and error. So instead of assuming that this is top and bottom, you can try sweeping this horizontally, and let's see what happens. So here we have this, let's draw it again. We have this graph, right? And then we have this one line parabola right here, and we have this another line, straight line, like that. So you can try sweep the area here horizontally and see what happens. So you sweep from the left to the right, left to the right, left to the right, left to the right. Okay, it seems like we are able to sweep the whole region using the horizontal sweep. But if you look closely, there is a problem with this kind of sweeping. You can see here that at the bottom, you sweep from one function to itself, right? So here we have this one function on the left and this same function on the right. And if you put these two same functions in the integration, it's going to mean that the left hand function and the right hand function is the same. So this is going to create the integration become 0. Become 0. Well, if you do this straightforwardly, it's going to come out to be a problem. So don't do it. In this case, you can see right away, hey, I sweep from one function to itself. That's not going to work, so let's forget about this approach. And we are going to stick with the type 1 that we see in the beginning. Okay, so type 1, once we know this, we know right away that we are supposed to integrate this one value with respect to y first. That is why we need to know the type. That's because we need to determine which variable to go first. And then here we know it's y. Now we integrate with respect to x. So in this case, integrate with respect to y first, we need to integrate from lower function, which is g1x, to the upper function, g2x. Now, for the second integration, the x variable, we need to sweep the whole region. So A and B. Now, let's find out about A and B. We need to find out about this whole region of x sweeping. Like, at this point, we don't know these intersections, so we don't know the whole range. So the first thing we need to do here is to find these intersections and see where it happens. So we have two lines, y equal to x squared and y equal to x plus 2. We want to find the intersections of these two lines. It means that we have to solve these equations at the same time. So I'm going to substitute y equal to x squared to the second equation. So this becomes x squared equal to x plus 2. And move things around, x squared minus x minus 2 equal to 0. And do some factorization. And you are going to see that this is x minus 2 and x plus 1 equal to 0. So from this equation you solve this and you get x equal to minus 1 and 2. In this case, you don't need to check the validity of your solutions because you didn't square both sides. So when you didn't square both sides, there is no problem with the signs. So here, both of them would work here. So the first x happens at minus 1, x equal to minus 1, and y equal to what? Just plug minus 1 into one of the equations. Let's say I try the y equal to x squared. So y equal to minus 1 squared. So that is 1. That is the first coordinate of the first intersection. Now the next one happens at x equal to 2, and I plug in 2 into the equation. I get y equal to 4. So now I know the range of the x starts from minus 1 and ends at 2. So A equal to minus 1 and B equal to 2. Now what about g1x and g2x? g1x is the lower function. So lower function, you can see that this is the parabola. So lower function is parabola, which is equal to x squared. Okay, and for g2x, that is the upper function. And as you can see, g2 is this, y equal to x plus 2. So g2x is x plus 2. Okay, I need to save some space. So let me put this right here. g2x equal to x plus 2. g2x equal to x plus 2. Now that we have everything, let's put this back to the double integration. So this is equal to integration of a to b. So minus 1 to 2, the whole range of x. Now the lower function and the upper function. So this is lower function x squared. Upper function is x plus 2. And we want to find the area, right? So the function value that we want to use here is 1. And we sweep y first because this is type 1. And then we integrate with respect to x. So here, integrate. Let me put some space here. Okay. Now this is equal to integrate y with 1 with respect to y. So this is y, and we have to evaluate at x squared and x plus 2, and integrate again with respect to x from minus 1 to 2. So this is equal to x plus 2 goes in as y, x plus 2, minus x squared goes in as y, minus x squared. Alright, and I need to integrate this with respect to x from minus 1 to 2. Okay, and if I continue, this is going to be x squared over 2 plus 2x minus x cubed over 3. Alright, and then I have to evaluate this at minus 1 and 2. And I'm going to cheat on I'm going to cheat at this step a little bit by using the calculator. So I plug these numbers into the calculator, and the result I get here is 4.5, and that is the area of the region in example 7. So don't forget the unit here, square unit. And that is another example on how to use the double integration to find the area. It's all about this formula. And the key is to specify to make the function value be 1. Once you do this, the formula becomes the area. Okay, so this is the end of lecture note number 10. And homework will be assigned to you this week, and I give you 7 days to work on the homework. It's going to be due next week, and after that it's going to be lecture number 11. So I'm gonna see you guys again in the next video. Alright, see you.